Welcome to This Explainer. Have you ever actually stopped to think about how we see the world around us? It all comes down to one of the most fascinating phenomena in the universe, light. To give you a sense of just how wild light is, consider this. Because it travels at the absolute speed limit of the universe, from a photon's own perspective, it experiences absolutely zero time. Today, we're going to trace the epic journey of a single ray of this timeless energy. By understanding how this one ray behaves, how it bounces, how it bends, and how it breaks apart, we can unpack the hidden mechanics behind everything our eyes perceive. It's like the ultimate cosmic journey, and I'm absolutely thrilled to be your guide today.
Okay, let's dive right in. Here's our roadmap for today. We're going to look at the nature of light, the rules of reflection, mirrors and virtual images, refraction, which is all about bending and speeding up, optical illusions in water, and finally, dispersion, or splitting the spectrum. Let's get to it. Starting with Section 1, the nature of light. So, I've got a question for you right off the bat. Is light an electromagnetic wave or a mechanical wave? Think about it. How does light actually travel through the vast, completely empty vacuum of the universe to reach our planet? Does it need something physical to ripple through, kind of like how sound needs air or water?
Well, the answer is that light is a transverse electromagnetic wave. And honestly, that's a huge deal. It means it absolutely doesn't need a physical medium at all. Instead, it travels by self-propagating, oscillating electric and magnetic fields that basically leapfrog each other right through empty space. Plus, light has zero mass, literally 0 grams. Because it's pure energy, it travels in perfectly straight lines at a truly staggering speed, 300 million meters per second. Just let that sink in for a second. At that speed, our light ray is the ultimate cosmic sprinter, zipping through transparent materials and the vacuum of space alike.
Moving on to Section 2, the rules of reflection. Now, what happens when this insanely fast light ray hits a roadblock it just can't pass through? When the incoming light, the incident ray, strikes a flat mirror, it bounces off as a reflected ray. Now, you might be wondering about that imaginary perpendicular line right at the point of contact. We call that the normal. We use it because real-world surfaces can be curved, right? So we measure from this perpendicular line to keep things totally consistent. And the golden rule here? It's an unbreakable law of physics. The angle of incidence, marked as I, perfectly equals the angle of reflection, marked as R. It is a flawless, symmetrical bounce. So obviously the direction changes, but how does that bounce affect the light's core properties? Well, the speed of a wave is entirely dictated by whatever medium it's traveling through. Since the light just reflects back into the exact same air and doesn't pass into a new medium, its speed doesn't change at all. Its wavelength remains exactly the same. And its frequency completely remains the same too. The light itself is totally unaltered. It's literally just been redirected.
Which brings us to Section 3, mirrors and virtual images.
When you stand in front of a standard flat, plain mirror, the reflection you see follows some very specific rules based on what we just talked about. The image is exactly equal in size to the object, it's upright, and the distance from the object to the mirror is completely equal to the distance between the mirror and the image appearing behind it. And finally, the image is what we call virtual. That means it's at the same level as the object, but you can't actually project it onto a screen. Why does it look like it's behind the mirror? Well, our human brains evolved to assume light always travels in a perfectly straight line. So when those bouncing rays hit our eyes, our brain forcefully traces them backward, right through the solid wall of the mirror, constructing this phantom image in our visual cortex. And while the image is upright, it is completely reversed horizontally. We call this being literally inverted. Think about the geometry of holding up a piece of paper with the word B written on it. The points on the letter closest to the mirror reflect back first, making them appear closest in the reflection. That geometric timing results in lateral inversion, a direct geometric result of those perfect angles of reflection bouncing straight back at you.
All right, Section 4, refraction, bending and speeding.
This brings us to refraction, which is simply defined as light bending as it goes from one medium into another. But why does it bend? It bends entirely because it changes speed. At a microscopic level, as the wave forces its way into glass or water, its photons suddenly interact with denser electron clouds, and that delays the wave's overall propagation. It's kind of like a runner sprinting on a smooth paved road who suddenly runs at an angle into thick, deep mud. The leg that hits the mud first slows down while the other leg is still moving super fast on the pavement. That sudden change in speed forces the runner's body to pivot and bend its path. Light does the exact same thing. Let's compare these two scenarios. On the left, light enters a denser medium, like going from air into glass. Because it hits that denser stuff, it slows down. And when light slows down, it always bends towards the normal line. Now look at the right side. Here, the light is escaping the glass and going back out into the less dense air. It speeds up, and because it speeds up, it bends away from the normal line. So the change in density dictates the speed, and the speed dictates the exact direction of the bend.
But there is one absolutely critical exception here. If the light ray hits the boundary completely straight on, what we call incident normally, the angle is 0. Because the entire wavefront hits the denser medium at the exact same fraction of a second, the whole wave slows down simultaneously. Without one side slowing down before the other, there's absolutely no pivot. The angle of refraction is 0, so there is 0 bending, just a change in the light ray's speed as it pushes straight through that denser glass.
Now, contrast this with reflection. Because the light is passing through an entirely new medium, its speed absolutely changes. And because the speed changes, the wavelength changes too. However, and this is super important, the frequency of the wave brilliantly stays exactly the same. You can think of frequency as the heartbeat of the light wave. It's permanently set by whatever atomic source created it, like a star or a light bulb. The medium can stretch or compress the wave's strides, it can change its pace, but it absolutely cannot alter that fundamental heartbeat.
Next up, Section 5, Optical Illusions in Water. I've got another question for you, setting up a classic, mind-bending visual illusion almost everyone has seen. When you look down into a pool or a lake or even just a glass of water, do we actually see objects in their real position?
No way, we definitely don't. Take a look at the path of the light traveling from the fish to the observer's eye. The fish is actually down at its real depth, but as the light reflects off the fish and travels up through the water, it hits the boundary with the air. Because air is less dense, the light speeds up and bends away from the normal. But remember, our human brain stubbornly assumes light travels in a perfectly straight line. So your eye traces that refracted ray straight back, creating a virtual image of the fish at a much shallower apparent depth. This exact illusion is why archerfish have to calculate complex internal trigonometry to spit water at bugs above the surface, and why spearfishermen have to intentionally aim below where they actually see the fish. It's a total trick of the eye.
And finally, Section 6, Dispersion, Splitting the Spectrum.
Check out the prism mapped out here. This is dispersion. It happens when white light enters a specifically shaped medium, like a triangular glass prism. Because of the angles of the glass, the refraction we just learned about gets completely amplified. That single beam of white light is separated, shattering apart into the beautiful 7 colors of the visible spectrum: red, orange, yellow, green, blue, indigo, and violet.
Let's break down exactly why this separation happens. It really all comes back to speed, wavelength, and atomic interaction. When the light hits the prism, violet light, which has a higher frequency, interacts way more energetically with the atomic structure of the glass compared to the lazier, long-waving red light. That extra interaction slows the violet light down far more than the red, causing a much sharper pivot. So because it has the shortest wavelength and highest frequency, violet becomes the highest refracted ray. The prism is literally sorting the light perfectly by its wavelength. How cool is that?
We've seen light bounce perfectly off mirrors, bend through dense water, and shatter into a rainbow inside a prism. But I want to leave you with one final provocative thought to ponder as we wrap up. If a light ray's speed fundamentally slows down when it hits water or glass, what happens to its speed when it escapes the Earth's atmosphere and re-enters the endless vacuum of space? It immediately accelerates right back to its absolute maximum speed of 300 million meters per second, continuing its eternal journey across the cosmos completely unchanged. It's a true testament to the incredible, enduring laws of physics. Thanks so much for joining me on this explainer today, and I really hope this leaves you eager to explore even more hidden wonders of our physical world.